So Gisela comes from Argentina. Again, when I was looking for people on a project company, founder to Guillermo again. But Gisela also organizes this virtual seminar that is called Enocas of non-commutative algebra seminar or something. But she has been running it for a long time.
That the name is
and so she's been in charge of that. Shows somehow her interest and also in socializing mathematics. So Gisela, thank you very much for coming and Coinduction for comodule.
Yes, thank you very much, Bernardo. Thank you for this invitation. It is also my first time in conference in the United States.
Really?
Yes, so I'm very glad to be here. And well, I want to talk about this is an ongoing project with Eugenia Ellis and Ana González. They are both from Uruguay. And this is about coinduction for comodule algebra. So let me start recalling the construction for groups. That is, if we have a group G, it's a group H, and we know an algebra with an action of H. So how do we get an algebra with an action of the whole group? This in algebra. So G is the group, R is an algebra. So a left action of the group G on the algebra R is given by a group homomorphism, and this will be the notation for left action. G acting on the left of R. And in this case, we call R a left G algebra. So now we have H as a group of G, and by the projection map to the right cosets. So for any left H algebra R, so we have an algebra R with the left action of the subgroup H, we can construct an induced left G algebra. This is done in the work of Eugenia and Morita. So this induction algebra is the algebra of functions from the group G to the algebra R, which satisfies these conditions. The first condition is that this function must be supported in finitely many cosets. And then we have this condition. T is an element of the group G, H is an element of the group. So note that this tells us that if we know the value of F in some representative of the right coset, then we know the element of F on the whole coset. And the left G action on this in algebra is given by the following formula. G acting on the left of the function F, and we evaluate on T just F on TG. This is the group form. So this acts on the left, enters on the right. This construction is functorial, so we have actually a functor from the category of H algebras to the category of G algebra, and it satisfies this property. For example, if the algebra R is already a G algebra, then we just recover the original algebra or an algebra isomorphic. If the algebra has a trivial action that is an action of the trivial subgroup of G, then this in algebra is that the algebra of functions from G to R finitely supported. Now, what happens if we put here what for me is the trivial algebra? Here I put complex numbers because I'd be interested in complex coefficients, but we can put here any commutative unit array. Okay. So if I put the complex numbers, then this in algebra is the algebra defined on right cosets and also finitely supported. So in this case, in case that the algebra is the complex numbers, this tells us that this function is constant because the action is true. Okay. Another interesting property is what happens if we take this algebraic cross product. Now we have a G algebra, a left G algebra. We take this algebraic cross product. Well, this new algebra is isomorphic to an algebra of matrices. This stands for matrices with entries in this algebraic cross product, we call that R is a left H algebra, indexed by the cosets and with finitely many non-zero entries. Okay. And this result is a result that Eugenia mentioned yesterday. So these are algebraic KK groups. And this in functor is left adjoint to the restriction functor at the level of KK. So now note that an action of the group G on an algebra R can be extended to an action of the whole group algebra R. And moreover, if we consider the group algebra as a Hopf algebra, then R has a structure of a module algebra over this Hopf algebra. So let me recall the definition of the Hopf algebra and an action of the Hopf algebra because I need to pick some notation. Okay. So what is a Hopf algebra? I will speak about Hopf algebras over the Hopf. So a unital complex algebra H is a Hopf algebra if it is equipped with, well, first we need an algebra homomorphism, which is the multiplication delta from H to the tensor product of H with itself. And this multiplication must be co-associative. So this is the condition for co-associativity. And this condition allows us to use what is called the Swidler or sigma notation. So I will write delta of H as H1 tensor H2. So this stands for a finite sum of elementary tensors. Okay, there's a finite sum implicit here. So we have the co-multiplication, we have the co-units, an algebra homomorphism for the co-units that goes from the algebra to the complex numbers. And this is the condition for the co-units. Every element H of the algebra can be written as epsilon of H1, H2, or H1, epsilon of H2. Again, here we are using Swidler notation. And finally, we need a bijective anti-algebra homomorphism, which is called the antibode from H to H, and this is the condition for the antibode. Okay, so our example of Hopf algebra is the group algebra. So we take any group G, groups are discrete, we take any group G. So the group algebra is a Hopf algebra with this structure. The multiplication is given by the diagonal. So these are group-like elements. The co-unit on an element G is always 1, and the antipode is just taking the. Now, if our Hopf algebra is finite dimensional, then we can take the dual, that is linear functionals from H to the complex numbers, and we obtain again a Hopf algebra. Now the product in this dual is the convolution product. So F star G evaluated as an element H is F of H1 G of H2. The co-units of the algebra is epsilon is the co-units of H. That's the units of the dual. And the co-multiplication of the dual is obtained by transposing the multiplication of the algebra. So the co-multiplication on F, this is an element of H dual tensor H dual. So we evaluate in a pair HK of elements of the algebra, and that is just F on H. And the co-units of the dual, the co-units evaluated on F is just F evaluated on the against of the algebra. And in this case, I mean finite dimensional Hopf algebras, we have the following result. If we take the dual again, we will recover the original. So we have like a good duality for finite dimensional Hopf algebra. Now, so note that if the group G is not finite, the group algebra is still a Hopf algebra. But we have problems with the dual, because in this case, the dual gives us all the functions from G to the complex numbers. But it's not a Hopf algebra because if we want the commutaplication to be the transpose of the multiplication, note that this M star now takes values in the dual of the tensor product. And as the group, if the group is not finite, this is not a finite dimensional algebra. So this tensor product of the dual is strictly contained generally in this bigger algebra. So we have problems defining the commutaplication of, that is, we have problems if we have a non-finite dimensional algebra with duals. So what about actions of Hopf algebra? Well, Now we have H, our fourth algebra, R a unital algebra, and we say that R is a left H module algebra if, well, R must be an H module. That's the left action of the algebra on R. And we have also these conditions. An element H acting on the product RS must be H1 acting on R times H2 acting on S. Here also there is the Sweeter notation for the element of algebra. And H acting on the identity of R must be the co-units on H times the identity of S. So what we have, if G is a group and R is an algebra, then we say that saying that R is a G algebra is the same as saying that R is a module algebra over the group algebra seen as a coalgebra. Okay. So let's recall our inductive algebra. If we are given H as a group of G and R an H algebra, this construction of the induced algebra is a special case of induction for algebra. Namely, we know how to induce actions if we are working with group algebra. Now, for finite dimensional group algebras, we have a relation between actions of the algebra and coactions of the dual. So let's recall what is a coaction of algebra. So H is a Hopf algebra, R is a unital algebra, then R is called a right H comodule algebra if there exists a linear morphism rho from R to R tensor of algebra such that it verifies this condition. Here is the first condition, and look at for the second and the third one. I'm also using Sweeter notation for coactions. This R0 tensor R1 means a finite sum of elementary tensors of this algebra. Okay. So the first example of coaction is just take the Hopf algebra with its multiplication. Note that this condition, if we put rho equal delta, is just the co-associativity of the multiplication. Okay, now for finite dimensional Hopf algebras, we have the following result. R is the left H module algebra if and only if it's the right comodule algebra over the dual. Here I speak about left actions and right coactions, but it's the same if we take right actions. So, for example, if we consider H as a right H comodule algebra with the multiplication, the left action of the dual is given by this formula. Functional alpha acting on H is just alpha evaluated on H2 times H2. And what happens for group algebra? Well, now E is a finite group. So here we are talking about finite dimension. Okay. So if G is a finite group, the group algebra is a finite dimensional group algebra, and the dual is the algebra of functions from G to R. So given an action of the group algebra, this is the left action of the group algebra on R, the associated right coaction of the dual, i.e. gamma, is given by the following formula. Gamma on an element R is the sum over every element of the group. Okay. Here we put G acting on the left on R tensor, and this is the characteristic function of the element. Okay. And reciprocally, if we are given the right coaction of this dual R, this is the notation for the coaction, the Sweeter notation for the coaction, then the associated left action of the group algebra is given by the following formula. The action on R is R1 evaluated on G times R2. So this is similar. So, but what happens if our group is not finite and we want to induce coaction? Because if the group is finite, the group algebra is a finite dimensional algebra, and for us it's the same working with actions of the Hopf algebra and coactions. If the group is not finite, how can we induce coaction? So the idea is to work in the framework of algebraic quantum groups. Why algebraic quantum groups? Because they have a good duality, like in the case of finite dimensional algebra. You have an algebraic quantum group, you can construct a dual, which is again an algebraic quantum group. And if we can take duals twice, we will cover the original algebraic quantum group. And we also have a result about action or so we can consider the group algebra as an algebraic quantum group is G. In this case, the dual as an algebraic quantum group is the algebra functions from G to complex numbers, but which has finite support. This is contained in the whole dual that is all function. So this G hat is again an algebraic quantum group, and this is the duality results that resembles the case of finite dimensional of algebras. So we take dual twice and we recover the original quantum group. If we have the left the algebra, the algebraic quantum group, then R is an equivalent only. R is a right. It has comodule algebra. I will say what is algebraic. And we also have this kind of duality. Note that here we have algebraic paving theory and for algebras which are algebras over an algebraic quantum. These groups were defined by Eugenia. And as we've got this good duality, we can think of algebras over the algebraic quantum groups, and we can also think of algebras over the dual, which is again an algebraic. So we have this kind of back scandalous duality. And actually, this is our motivation for working with algebraic quantum, or in that of coactions, because we want to obtain results in algebraic. So, what is an algebraic quantum group? It's a regular multiplier of algebra 8 with non-trivial invariant function. So I will explain what is a regular multiplier of algebra and what is an invariant function. But first, let me tell you that every Hopf algebra is a multiplier of algebra. That every finite dimensional Hopf algebra is an algebraic quantum group. And that for every group G, the group algebra is a multiplier. Okay, so I will, instead of giving the precise definition of regular multiplier of algebra and invariant functionals, I will explain the structure of this group as an algebraic of this algebra. So G is the group. This is my notation for functions from G to the complex numbers with finite support. Okay. This is an algebraic quantum group with the following structure. So we need multiplication. In this case, multiplication is given by multiplying the characters function. This is the factor delta. We need the multiplication, but note that the multiplication now is allowed to take values in the multiplier algebra of this tensor product. What is the multiplier algebra? Well, if we start with an algebra A, the multiplier algebra, we have to ask the product in A must be non-degenerate. The multiplier algebra is the universal unital algebra that contains A as an essential two-sided ideal. So, if A is already unital, the multiplier algebra is just A. Okay? So, we allow the multiplication to take values in the multiplier algebra. In this case, the multiplication is given by this formula. The multiplication function is the sum over every element in the group of this tensor product of characteristic functions. So that this is not an element of the function. It is actually in a multiplier.
Like formal series? Just I don't understand what is by algebra.
It's the set of left and right multipliers. The idea is you can think of an element of A. An element of A is a linear function from A to A, which is just multiplied to the left. But you can also think as the elements of A by multiplying to the right. So this is constructed as the pairs of all left and right multipliers. Functions from A to A that behave similar than multiplying on the left and on the right with elements of A.
You said A is fundamental,
This is A, the multiplier algebra is A.
so in this case, it's just the ordinary tensor product.
Yes. So
No, it's not. There's no unit.
Oh, isn't there-
in this case, no. So if your algebra is unital, the multiplier algebra,
Why isn't there any unit? Sorry.
because we need finite support. Finite
Oh,
support
oh,
functions.
finite.
Yes. In this case, it's a multiplier.
So this is not like taking any serious or any infinite product, it's something different.
And well, the multiplication must satisfy this condition. The first condition is that every time we have an element of the form delta or an element of the algebra multiplied by this one here stands for the unit of the multiplier algebra. Maybe I should say that if you, this is the multiplier algebra of an algebra. What happens if you have two algebras? Have an algebra A and algebra B, both with non-determinate product. Then we can take the multiplier algebra of A tensor B, but we can also take the multiplier algebra of A tensor the multiplier algebra of B. And this inclusion is compatible with this. Okay. So the one that appears there, here, and here is like we're taking the unit here. And so we need that these type of elements actually are elements of the tensor. Okay. And we also co-associativity. Note that here I'm using a different notation because the image of delta is contained in this multiplier algebra. But this morphism is defined on the tensor product. Okay, so what we have to do is to extend this morphism to the multiplier algebra. We can do this under certain conditions. And also here, this we first must extend this morphism to the multiplier algebra. We also need a co-unit and an antipode. The co-unit is an algebra morphism from our algebra to the complex numbers. In this case, the co-unit is given by this formula. So the co-unit on a characteristic function is 1 if the element is the neutral of the group and it's 0 otherwise. And the antipode is the bijection is given by, in this case, is given by this formula. Okay. So the co-unit and the antipode must also verify conditions. Note that now this delta A tensor times 1 tensor B, this is an element of the tensor product because of our condition multiplication. So we are applying the co-unit tensor identity to this element and we will recover AB. Similar here. This is an actual element of the tensor product. Okay. Note that if our algebra is unital, we can put B equal the unit, and we recover the condition for the co-units of the co-algebra. Okay. Similar here. So I can put A equal the units of the algebra. This is just the condition for the co-unit. The same for the antipode. Okay. We have to write the conditions in terms of this element because of the multiplication taking values. But in the unital case, this is just the co-units and the antipode for algebra. So if we have an algebra with a multiplication, a co-multiplication, a co-unit, and an antipode which is bijective, what we have is a regular multiplier of algebra. This regular here means that actually the antipode takes values in the algebra and is a bijection. If we don't ask for regularity, we just get an antipode from the algebra to the multiplier. Okay? But we ask for we work with regular multiplier of algebras, so the antipode is actually adjunction. So this is the natural extension of the notion of algebra for the non-unit.
Does it induce a algebra structure in the multiplier algebra?
A algebra structure in the multiplier algebra is.
Yes, all this, does it generate one?
Yeah, well, we can extend morphisms to the multiplier algebra.
So then, yes.
Yes. Yes. But we also need, for having an algebraic quantum group, we need invariant function. So which is an invariant function? Well, it's a functional from the algebra complex numbers, which satisfies this problem. Okay, here I write the condition for the left invariant function. If we put here phi and here the identity, what we get is a right invariant function. In this case, the left invariant functional is given by this form. Note that if we have a left invariant functional and we recompose it with the antipode, what we get is a right invariant. So having right or left invariant functional, we can compose with the identity and pass from left to right. And also, if there exists a left invariant functional, any other left invariant functional is a scalar multiple. So this, for me, resembles the case that for finite dimensional algebra, the space of left or right integrals have an equal. We can go from left integrals to right integrals using the So we have an algebraic quantum group, okay? And this is the general definition of algebraic quantum group. This is our example. Now, how do we construct the dual of an algebraic quantum group? So we have to pick a left invariant functional of our algebraic quantum group. But then for every element in the group, we write phi sub x for this new function. Phi sub x on y is just phi evaluated on xy. And the dual quantum group, this hat, is defined as the space of all these functions. Okay. Now I pick a left invariant functional. This is the same if we pick a right invariant function within the same space. We can work with the left or with the right invariant functional and do this construction. This is the general construction for the dual of the right. And well, we regard this space as a subspace of the dual. These are all functional. And take the dual of the product and the coproduct of our algebra, and we obtain a product and the coproduct on this dual. So this is an algebraic function. We can also construct invariant. In this particular case, this dual can be identified with the Hopf algebra. This is the group algebra, okay? With its usual multiplication, the diagonal, and which is the invariant functional in this case. Well, this phi hat evaluated on an element of the group is just the delta product. It's 1 if G is the neutral element and 0 other. So we have to do it. Now we want to induce GOR. So we take H is a group of G and write the projection. These are functions from G to the complex numbers with finite support. These are functions from H to the complex numbers with finite support. And this is the way of seeing this algebraic quantum group as a sub-algebraic. Have to take the projection. So the idea is how if we have an algebra over this algebraic quantum group, how we can induce an algebra over this. So the first thing to do is to consider C sub C of T as a left comodule algebra over this algebra. And the coaction is given by the multiplication composing these five tensor identities. In this case, we can explicitly write what it is. So this delta goes from this algebraic quantum group to the multiplier algebra of the tensor product. I didn't write the definition of the coaction of multiplier of an algebraic quantum group. It's the same as in the case of algebra, but we allow this morphism to take values in the multiplier. So in this case, we have delta evaluated when a characteristic function is the sum over every element in the subgroup H of this tensor product. So we have to apply the multiplication, and then we apply phi to the first tensor. This again is an element of the multiplier algebra because the sum runs over every element of the sum. Now, suppose we have both R is a right CC of H comodule algebra with some coaction, which I call rho, and the coaction of the integral. Okay. So this is the construction for the induced comodule algebra over CC of G. What we take here is the cotensor product. That is, elements X of this tensor product are tensor C sub C of T, which verifies this equality. It's like an equivalence. And well, this result that we have an induced algebra. This is a right C sub C of G comodule algebra, and the coaction is given just by taking the commutaplication in this part of the tensor and the identity of R. So we can prove that this is in fact a comodule algebra over CC of T. Okay, and the properties that this verifies are similar like in the case of groups. For example, if R is already a C sub T of T comodule algebra, then we'll cover an algebra marked to R. If we start with an algebra with a trivial coaction, then we get the algebra of functions from D to R, which are finitely supported. That C here stands for compact support. Discrete case. Oh, so let's see what happens in this example. Let's consider trivial comodule. That is, we consider the trivial right coaction of C sub C of H on the complex numbers. So this is a trivial coaction. We send a complex number to the number tensor 1. This is an element of the multiplier algebra. And by definition, our induced comodule algebra is given by the cotensor product. Okay. So in this case, we can identify this algebra with the subalgebra of coinvariance for the coaction. This is the coaction that we defined previously, and by definition, the covariance for the coaction are elements of the algebra, such that when we apply the coaction, we recover the identity terms for the element. So we know what it is in the case of the trivial algebra itself, the subalgebra of covariance. And the subalgebra of covariance, what will be the usual right coaction? We just restrict the commutaplication of CCO. So we have a right coaction of CC of G, then we must have an action, a left action of the dual, but the dual is just the group algebra. What is the action of the group algebra? Well, an element K of the group acting on an element of this induced algebra is just, this K multiplied inverse K multiplied in the characteristic. This is the left action of the group. This case is. Now, if you remember when I talked about the induction for groups, we have the result about the tensor product. The induced algebra with the group, there is an isomorphism with matrix. So we want a similar result. It's like a Morita equivalence. So I have to talk about the smash product instead of the algebraic. And for talking about the smash product, it's easy to use the Switzerland notation. So first we have to extend the Switzerland notation of algebras to the case of algebraic quantum group. So the DB and algebraic quantum group. The point is that the usual Switzerland notation can be extended to this case. So now in general, this element delta of x is not an element of the tensor. This lives in the multiplier algebra. But the point is that we always have that these elements, delta x times 1 tensor y, this is an element of the tensor product. So we will write x1 tensor x2y for this element. And we can extend this notation because for algebraic quantum groups, we have local groups. So with some care, we can use this notation. Okay. We cannot write delta x as x1 tensor 2, but if we have these kinds of elements, we can use it. So given a left D modular algebra R, we can define the smash product algebra as follows. The underlying vector space is just the tensor product in the case of algebra, and the product is given by this formula. So we put R, x1 acting on the left on R prime, smash x2 y. If we have a coalgebra, this is okay. So what is our result about Morita equivalence? Well, if we have a group G and a finite subgroup, have to ask the subgroup to be finite, then well, an R a right comodule algebra over C sub C of H, then we have this Morita equivalence. This induced algebra smashed the group algebra is Morita equivalent to R smashed the group algebra over H.
In what sense Morita equivalence only that the modules in some category?
In the sense, yes, we are going to construct two bimodules to the tensor product and obtain bimodulizing office.
Modules
I will,
of algebraic quantum group.
no, module, just module. This is an algebra. This is no longer an algebraic
So
construct.
Morita equivalent as algebra.
As algebra, as algebra. I will explain the construction in the case of the trivial algebra. So, in the general case, these are the bimodules. I will explain what happens if we take the complex numbers because this is the known algebra. So, if we put R the complex numbers, the previous result says that this group algebra is Morita equivalent to this smash product. Recall that H is finite. So the Morita context is given by these are the bimodules, and this will be gamma and lambda will be the algebra. So we have that the group algebra over G has a left action of the group algebra, which is over H just by the H with the group. H is a group of T, and it has a right action of this smash product. So this acts, we just evaluate X at G, and then to G times. So X lives in this algebra. Okay, we can evaluate. And then we have C sub E of T, that is the dual. This is the algebraic quantum group. This is the dual. Okay? As the bimodule with this structure, with these actions. Now the smash acts on the left on this algebra. So how does it act on characteristic function? Well, we just C enters here, multiplying with its inverse, and we just take the multiplication of elements. And then we have a right action of the group algebra over C, H acting on the characteristic function on the right. Is like this. We take the characteristic function of H inverse G. So these are the bimodules, and these are the isomorphisms of bimodules. So we have to take the tensor product, in this case is over the smash product, and we see this as a bimodule of this group algebra. And in the other case, we do the other tensor, we do the tensor over now this group algebra, and this is a bimodule over the smash product. These are the formulas for the isomorphisms. These are isomorphisms of bimodules. And they also have to satisfy this compatibility.
So I have only one word, which is
Yes.
on the top, there is an H, right, on left, on the forward.
Yes.
And on the Morita context, there is no H. See the two.
This, no, the
modules.
module doesn't involve age.
Of course.
Look here. The module. You check this, and this is the algebra with an actual age.
So this is a universal module. You don't have to put in subgroup and then.
Yes.
We work equally.
Fine. Fine, yes. So we have the, yes, it doesn't depend on the subgroup that we take final. So these sums are over the elements of H, which is fine. And these are the compatibility conditions that satisfy for the Morita complex. Because, well, that is what I wanted to tell you today. Look at, these are our references. Here, in this paper, a new approach to induction and we are really here. An algebraic framework for group duality. These were algebraic quantum groups are defined. And in this work, a new approach to induction and impermittivity results, there are some results of induction, but for locally compact algebraic quantum groups. That is for Neumann algebra. Okay. So we want to obtain, so we were inspired in this paper to obtain results in the case of algebraic quantum groups. So far we have these results for these kinds of algebraic quantum groups. Okay. CC of G with the algebraic quantum group CC of H. And we have a construction, a candidate for a construction. So what is next? What happens if we take another class of algebraic quantum groups? For example, if our algebraic quantum groups are finite dimensional. Well, finite dimensional algebraic quantum groups are just covalent. Okay, so that will be our next step. What happens with algebra? Does this induced algebra is the correct induced algebra? And by the correct, I mean, do we have a Morita equivalence? Okay. Another thing that we can think about is does this in what part is this function, and that if it is a function, it is adjoint to the restriction function algebraic KK theory for algebraic groups. And what else can we say about this at the level of algebraic KK theory? So that's our ongoing project, and we hope to have more results to tell you later. So that is everything I want to say today. Thank you.